Hello? Hello? Well, first of all, let me thank you to the organization of SEC Paris. I think they did a great job, especially with the circumstances that we are. So I just want to ask you for applause for the. Well, let's start. I'm Jordi Baylina. I'm the technical lead at Hermes. For the people that don't know yet what's Hermes, Hermes is a layer 2 rollup, a ZK rollup. It's launched. It's actually running in mainnet. The people of you that have been playing to the Trust community game, they were using the Hermes rollup in mainnet. So you can do if you have any ERC20 token and you want to do transfers in a cheap way, Hermes is already running in there. It's a rollup that's decentralized. The protocol is fully decentralized. We are doing a batch transaction every 10 minutes or so. It's the rollup that's the most efficient in terms of cost. The proof cost of the rollup is very, very, very cheap, and is the one that I would say the cost per transaction is the cheapest one. We also have been working in the interoperable with other rollups. It's still something that's working in progress. The rollup already from the security perspective, at some point it had $30 million, which is well, it's a good quantity just to start. Smart contracts never are safe, but that's at least if they have had $30 million and have not been hacked, it's better than if they don't have it. So that's something that's interesting there. From the more technical things, the prover of 2048 transactions, just generating a proof, we are around 1 minute, which is quite cool. Of course, we can run many provers in parallel, and we can achieve this scalability of 2,000 transactions per second. But this is already mainnet, okay? And the next challenge is going to be the ZK-EVM. That's actually what I'm going to talk in this presentation. Before going to the ZK-EVM, just a couple of things that we're also doing, and then I want just to share with you, is that we're also working with token swaps. We have a service for token swapping on Hermes, same way that you are doing with the game here, because it will be done a permanent service just to do token swaps. And then we also will work in the instant payments. But let's go to the ZK-EVM, okay? So we want to run smart contracts on a rollup. So we want to scale Ethereum mainly, that's what we want to do, okay? But why is it so difficult? It's just Ethereum Virtual Machine was not designed to run in a rollup, to run in a ZK circuit. Okay? It was designed 6, 7, 8 years ago, long time ago, and zero knowledge at that time. Very few people knew what it was. Zcash people probably, they are amazing people. They did a great work for that, so for the zero knowledge. So when we want to build circuits to run the ZK-EVM rollup, what strategies can we follow? Because it's not designed for, so we need to do some kind of engineering here. Well, there is one first, I would say, naive approach. So, okay, let's throw away Ethereum. Let's build a new Ethereum or a new VM that's ZK optimal to build on top of that. Okay, but what happened with all the knowledge that we have taken during these years, from security perspective, from writing smart contracts, from applications, etc. Okay, so another approach is, okay, we have this EVM. Okay, let's try to do it like Solidity compatible, or just we have a Solidity, we recompile the program. Instead of going to this EVM, we go to this other EVM. This has some problems, but something that's doable. And actually, some projects are doing this approach. Okay, but I want to explain like a third approach. That's actually the approach that we are following, and we are trying to just do it directly. So try to implement all the ZK, so all the opcodes of Ethereum directly in the ZK circuit. How we do that? Well, first of all, why opcode-based approach? Why do we want this compatibility between opcodes one-to-one? Well, first of all, from the engineering perspective, we have a perfect definition of the problem. We know the opcodes of Ethereum, they are in the consensus layer. So everybody knows what are those opcodes. So we know what's the goal. We know what we want to implement. We want to implement all the opcodes. So we want to, a person that has a smart contract circuit running in layer 1 should take this compiled circuit, put it in layer 2, and work exactly the same. That's the goal. And we do that if we implement all the opcodes. We want full compatibility with the ecosystem. If we do that, if we go at the opcode level, then we guarantee this compatibility with all the tooling and all the tooling that we have right now in the space. In the EVM, there is a lot of knowledge about security. So here, another advantage of doing opcode by opcode is that we maintain all the security model of EVM. If we have a new security model, for example, the gas, there is a lot of security in the calls. When you are doing a call, you are limiting the number of gas, and a lot of the security of smart contracts is based on that fact, because if not, you have reentrancy. Okay, so if you create a new EVM with a different gas model, what will happen? Well, we'll have to start over again on this. So if we keep this, you maintain the security that has been a work for many years on now. The other thing is that here, if you go to the compiled version, at the end, the efficiency, when we analyze the problem, it should not be that different, because Solidity is very much EVM focus. It's, in Solidity you have 256 integers. It's very linked, Solidity and the EVM. So at the end, you can, if you are doing in a Solidity way, you can end up that the compiler adds a lot of instructions of this specific zero knowledge there. And if you compare with the instructions that we are running in the way we are running, at the end, it's not going to be that different. So we don't see that a huge advantage, but something that we need to see in some way. Okay? And the last motivation that I want to add is because we believe in this solution. I think this is the right way to go. Maybe we are wrong, but we think this is the right way. So we go for it. Okay? So let me start to enter a little bit of the detail. So the idea is, okay, we cannot run, it's very difficult to create a ZK-EVM, an EVM optimal ZK-EVM directly running opcodes. So what we are doing mainly, the trick, and this is the important trick, is we are creating let's call it a micro opcodes. So we are creating like a kind of a EVM that's ZK compatible that interprets, that reads the opcodes and executes those opcodes on that. But the trick here is that this micro EVM that we are designing is very tailor-made for executing these EVM opcodes. And this is the way that we can optimize a lot. Okay? Just to set up the problem, at the end is we have a micro EVM assembly code. This could be like the ROM. It's a fixed program that we already have. The input of this program would be like the old state, all the transactions that we want to execute, and the output would be the new state. Okay, so that's like the program. So we have a program written in micro assembly, in micro EVM assembly, that reads the state, process all these transactions, and computes the new state. Just to set up a little bit the problem that we want to build. Okay, so well, here I'm going to jump. Okay, So well, I'm going to start going a little bit deep now. Okay, so. Before going a little bit deep, I just want to do like a 3 minutes parenthesis to explain a little bit about what's polynomial commitments, because this is very important to understand what's coming next. Okay? So this is, do not get scared, it's easy. So I think that most of you know what's a polynomial. You know, polynomial is something like that, okay? So a polynomial, oh, sorry. Polynomial can be, let me see if it's this, yeah. So polynomial can be, just here, it's a typical polynomial, a line 1 plus 2x, that's a polynomial, okay? So And in general, to represent a polynomial, we have the coefficients. So what's A1, A2, A3? This is the normal way most of the people understand what's a polynomial. Okay? But a polynomial can also be represented, but we will say the evaluation polynomial. For example, if we have a line, if we have 2 points, we also define a line. Okay? So if we have 3 points, we can have a 2-degree polynomial. So at the end, you just need evaluations to some specific points. Okay? So here is the coefficients representation, evaluation representation. And the cool thing here is that we have some interesting tools like FFT that you can convert from one numbers to the other. So I can convert, if I have a polynomial in the coefficient way, I can convert to a evaluation way and just switch, okay? So, well, polynomials, well, in general, you see it in the real space. In the real space, it's very easy. You just see a polynomial. Here we are in a finite field, so we don't have all the numbers. We just have a specific set. If we are, for example, working, for example, with a field of prime 17, here we just have only 17. So in the x-axis, we only have 17 values, and in the y-axis, we only can have 17 values. And this polynomial, if we evaluate this polynomial with the finite field is just doing modulus. You know, when you add the numbers and do the modulus 17. You multiply them and do modulus 17. So if you get this polynomial and you do the numbers, you can see here. For example, at point 0, 2 plus 3 plus 0 plus 0 plus 0, this is 2. Okay, so at 2, at 0, it's 2. So you can have just a normal polynomial, nothing fancy here. Okay? And yeah, this polynomial, for example, we can represent it with coefficients way. Just 2 plus 3x plus 6, 1, 1. So this is the coefficient way. But we can represent it also. This is exactly the same polynomial. This is in the evaluation polynomial. And we can convert from one to another just using this fancy function here. Okay? So we have polynomials. And then what's a polynomial commitment? Polynomial commitment is, okay, we have a prover and a verifier. So here we have an interactive protocol. The prover just commits to a polynomial. Committing to a polynomial is a little bit like committing to an array. So we can commit to all the evaluations to the polynomial. For example, a way of doing a polynomial commitment is just doing, in the last polynomial, is getting the 17 points, hashing them together, maybe with a Merkle tree, and sending this Merkle tree. So this is hashing the polynomial, okay? And then the verifier just chooses a random, chooses a random number, send it to the prover, and then the prover just, okay, at point R, what's the evaluation? Okay, this is what we call an opening. And so the evaluation at this point is whatever. Is at 0, is 2. Okay, it's 2. But how do you know that actually this evaluation at this point matches the commitment, matches the polynomial that you commit before? Well, here is you need to add the proof, and here there are some primitive, a lot of primitive, cryptographic primitive to do all these stuff. Okay. So this is what we call the opening a polynomial. And this is very cool because, well, this is an interactive protocol, but this can be converted very easily in a non-interactive protocol. So instead of waiting for the verifier to send a random number, because we don't have verifier, it's a non-interactive, what we do is we just hash the commitments that we made before. And because hash is an unreversible function, you cannot control this R. And you cannot control this R, you cannot cheat. And so you can build, you can have all the transcript, you can have all the polynomial commitments, plus all these proofs and these evaluations and this proof, and this just generates a zero knowledge proof in this case for this polynomial. Okay? So here is the math that I want to see. It's not hard. The cool thing here with this mechanism is that we can prove, so if I commit to 3 polynomials, for example, I can prove that, that there is some relationship between these 3 polynomials. For example, I can prove here that, I commit to A, B, and C. I commit that, for example, the polynomial A times the B is 44 times C x squared. So I can write any relationship between polynomials. Because if I add 2 polynomials, it adds to all the values. So I can do this. I can do these verifications of the polynomials. I can also do other kind of more interesting proof. For example, I can prove that an evaluation of one point matches the evaluation of the next point. For example, if I have in an evaluation this polynomial, I can check that the next value is the square of the last one. So I can do this kind of things, and there are some tricks to do this. Mainly you are doing is just opening two points, but you can do that easily in the polynomial commitments. We have all the tooling for doing this. Okay? You can, for example, prove that the polynomial at the beginning of, at some specific point has a value. Okay? But in here, and this is something new from the last years, And here, thank you very much to the Aztec people for the Blockup. There is one thing that's very interesting, is that you can prove that the evaluations of one polynomial are the same that the other polynomial, but maybe with a different permutation. They are different. Or even better, you can check that the points of one polynomial are included in another polynomial. Maybe there are some points that are missing, there are some points that are repeated, but you can prove that all the points, all the evaluations of one polynomial are the same to one polynomial. This is what's Blockup, and again, is here Zach and Ariel make a great work on that, and this primitive is essential for doing all what we are going to do next. Okay? So, okay, well, let's go back to the EVM. You know, the EVM, we have a lot of things to implement in the EVM. We have arithmetic, storage, binary. We have a lot of things. So as engineers, what we're trying to do is just trying to divide the problem in different things. Okay? So, well, let's start for the main program. You know, let's start for the CPU. Okay? So let's start the CPU in general. If it's a machine, mainly it's a state transition machine. So it's just you start from maybe some registers, a program counter. You just execute one function, you get a new states of the registers, and this would be a normal state machine that's executing a program. Okay? So a program written in assembly would be something like that. This is an example program. Of course, this would be the real program will be the program that actually reads, interprets all the transactions, executes all the opcodes and everything. Okay, but this is just a simple program of assembly how it would work. This is a program that actually it computes the fourth power of a number. In the first function, you just load like the input parameter. You just put one parameter in the A register, and here, well, you just create. You see here it's a loop. Okay, so you have a jump, and you decrement. You do these things 4 times, and then you are just multiplying A times A. Put it in A, and then you have 4 times. And when the end, it's just a stop. That's just an example program of the EVM, how it would work. Okay, so. Well, this is in assembly. We can convert these to some numbers. Okay, imagine that each instruction is one field number. We are working in a polynomial that's 256 bits. It's a huge polynomial. So we can have like a compilation here. Okay, so each instruction have like a codification. Some of these instructions maybe they have some constant value in there. For example, jumping, I need to say where I want to jump or something like that. So here you just compile. Okay, so this is just a field element. It's just a way of compiling this program. Okay, so what I have, if I put here, okay, let's run this program. Let's do a trace. What happened when I execute this program? Well, first I execute the first function. Registers are in specific status. I execute the move, and then this is puts the register B2 in this status, and this is like a normal state machine that's going. That's executing one of the other. As you can see, this state machine, we can define some relationships between the line A and the previous line. Okay? So this is just an execution trace. Okay? So and how this links to a polynomial? Well, I can take just all the values, for example, register A. Okay? Imagine that I say, okay, register A is a polynomial, and these are the evaluations of that polynomial. So this represents a polynomial. There is a polynomial register of A of x, where at point W1 is 0, at point W2 is 44. Of course, it's going to be a very high degree polynomial, degree as high as the number of lanes we have. It's a huge polynomial, but it's a polynomial. Okay? So here, I can convert all these trays in polynomials. Okay? So here is what you see in red here, that I convert everything in polynomial, okay? And what I'm building here is I'm building like I'm compacting. I'm just taking like 2 polynomials and composing them together. So I'm doing the program counter register, okay? And it's the first part of this. That's why I do 2 to the 16, the program counter, plus the instruction that I'm executing in the polynomial, okay? And in the main program, I'm doing a little bit the same. I'm just taking the position of the program and this position. And you can see that this polynomial here must be included here. So all the values here must be here if we are executing that program. Okay? So this is the inclusion using Blockup. The inclusion, this is what we are checking. So we are creating these polynomials. We are committing to these polynomials. And we are checking that the relationship between these polynomials are one the other. And with this, we guarantee that the instructions that are we executing are not some random instructions, are actually the instructions of the main program. And the main program is fixed. It's known by the verifier. You don't need to commit to the main program. The program is fixed. It's defined. So we can prove that this trace belongs exactly to this program. Okay? So we just do it with just a couple of polynomials, commit, we send. Okay? So this is the main thread, how it works. But there are more complex things. Okay, let's talk a little bit about the storage. How we do the storage? Well, instead of having like one single state machine, here we can have like different state machines. We have, for example, we have one state machines that compute as hashes, just one after the other. Just put whatever input you want here, and you just compute the hash. And maybe each hash has different steps. For example, Poseidon is like 60 steps. So, okay, you have a polynomial. It's just like a state machine that's computing the hash 60 times. When it finishes, just computes the next hash, and so on. We can have another state machine that computes a Merkle tree of the state. So in order to write a Merkle tree, you need to go twice. To go down just to verify the old value, and then the new value. And so you need to go up and forth to the Merkle tree. So for each step, you need to compute 2 hashes. What I do is, okay, I have a state machine that actually follows this, but instead of computing the hash in this state, what I mean is I'm assuming that this is okay. So I'm putting the hash that's the valid hash, but I'm just creating this polynomial. And at the end, so once I check that the hashes that I am assumed here as valids, that maybe are wrong, so I'm just putting the result. So I'm tricking. Here I'm tricking. But instead of putting so I'm just putting here. But then here is a polynomial, and then I'm checking that this polynomial is actually included in the polynomial that's in this other state. So I'm assuring that the hashes that I'm putting here are actually calculated in this other state machine. Okay? And again, let's go to the main thread. The main thread, we have some instructions that's going to be stored. Okay? Just maybe some of them read store, write stores, some stores. Okay? So it's very easy to build a polynomial that's 0 everywhere except for when you have a write. When you have a write storage. Okay? And then I can just check that the writes, the writes and the inputs and outputs of the writes here matches exactly the same that the inputs and outputs that are in this polynomial. And again, I'm using just Blockup just to match that this polynomial here is exactly the same than here. Okay? And with this technique, I can implement most of the opcodes. Because all the opcodes, they have a state machine that have a super state machine, and I just have all these polynomial commitments, and I'll link them one to each other. Okay? Let's go to memory. How I implement memory? Well, very much I'm doing the same. I have the main thread. Maybe I have a polynomial 0 everywhere except when I have memory reads and memory writes. Okay, very easy. And then I have a second state machine where it's memory. The cool thing here is that instead of just following the same order, what I'm doing is this state machine, I'm sorting the state, so I'm sorting the reads and writes first by address and then by a step. So, okay, what reads and writes are in the position 0. I have 2 reads and 3 writes, and I put those in the step order. So it's address, step. This is sorted by this. So in this state machine, of course, I need to check that they're following this order, so that this number is greater than the other one here. So this is included in the state machine here. And the cool thing is that then the relationship of this is very easy, because you just have one value, and if you are reading the value, and if you're writing that value. So you can have a very easy state machine on here. And again, how do I join those tables? And this is the cool thing. I can use Blockup, because if you just pack together the inputs and the outputs here that you are executing in the memory, and you pack the inputs and the outputs that you have in the main thread, this must match one. So this must be included in one and the other. So I can verify that the reads and writes that I'm really verifying, really doing here in this state machine are exactly the same that I'm executing in the my thread. And so go so forth. Just any upcode. No, I don't know. Doing pairings. Pairings. Maybe you have the final exponentiation. You have the Miller loop. The Miller loop have different steps. Each step may have some instructions. You have a sub machine that have instructions. The Miller steps may have like field 2. The field 2 will have field 1 conditions. So we can have a lot of sets of state machines, each one very specialized thing, and then joining them together. Okay? And this micro opcode, for example, is very useful also to do some in EVM, you have a lot of variable codes. For example, you have create code. Create code, you need to write, at the end, you need to write something in the state. But well, at the end, it's going to be a program that's going to take maybe from the data input, it will be somewhere in the memory, and we'll hash them together and write the state in the whatever it is. And it's a program. Okay? And you can implement anything. Maybe an exponentiation, a modulo exponentiation is a set of multiplications you can have. Okay? So you have a lot of state machines. They're going for many different things. And what you are doing is mainly this. First, you do the verification of each state machine holds by itself. If I'm doing memory reads and memory writes, this memory reads and memory writes. Okay? And second, I just verify this relationship between these different state machines by mainly using Blockup, so that this polynomial is the same or a permutation or included in this other polynomial. Okay, this is the main trick, easy. Okay? Okay, we have a bunch of polynomials, a lot. Okay, a lot of relationships. Okay, what happened with the verifier? Verifier is going to be expensive if we have a lot of things. So one of the concerns we have is, okay, we can do it maybe on chain. Maybe it's not that hard. Maybe it's not that cheap. We don't know yet, but probably, if the EVM is complex, so probably it's going to be a lot of gas here. So here we are considering two ways to pack these polynomials, polynomial commitments, and polynomial verifications. One of those is just using these Kate commitments and using Plonk, and especially Blockup, just for doing like, in Blockup you can verify, you can have like a lookup table in some way, so you can do like multiplications in the same field, and well, you can have some way to aggregate and just put everything with a single pairing in the verifier and then trying to aggregate. But this is, this is one way to do it. It's a little bit, I think it's more or less how the other people is doing. Okay, there is another way that we are analyzing and looks very promising right now. That's all these polynomials. Imagine that are Starks. Okay, so we can use, because Starks. No, Starks are great. The problem of Starks is that the proof of the Stark proof is huge. It's a lot, and you cannot put that in the EVM. It's very, very, very expensive. But imagine that we have growth 16. A normal ZK like Hermes circuit, or like any other normal growth 16 that's verifying Starks. So we can have a circuit as a growth 16 circuit that actually verifies, using a Starks, all these polynomial commitments, all these openings, all this relationship between polynomials, and using a Starks as the opening of itself. This has the advantage, because Starks has one important advantage, is that in order to write a verifier, you can use a single field element. So it works, so it's very easy to implement, so it fits very well implementing a Stark verifier inside a growth 16 or inside a Plonk, if you don't want the trusted setup. But the cool thing of this is that we can pack all these polynomial relationship that we saw before in, maybe it's a huge Stark proof, but all this proof is verified in another Stark. So at the end, in the EVM, only we have a single growth 16 or Plonk verification, which is 200, 300K. Gas. So we can prove a full EVM set of transactions, upcode by upcode, in the EVM with just a single verifiable system. And this is mainly what we are start building in Hermes, and we are very excited to do it in the upcoming months. Roadmap, when mainnet, I know that's going to be the next question. Of course, I'm not going to commit to anything. This is just the internal roadmap that more or less we have right now. But maybe it's sooner, maybe it's later. We are working on that. We are committed. We are going to work hard on that. That's at least in my side. So this is, but just to have some fear. So I hope that in probably less, but I hope that in the next year here we can present the ZK-EVM in mainnet. And well, that's it. I hope to bring the smart contracts. So I think I went quite fast. So I think we have some time for questions.
Hey, so you said you're upcode based. So in L1 Ethereum, when there's a hard, you need to add new opcodes. There's a hard fork. What's the equivalent in the ZK-EVM when you need to add the new opcodes?
Okay, a hard fork. Okay. If you have a hard fork in the layer 1, you will have two rollups running in there. So actually, you will fork also what's inside the rollup. That's the thing. If you don't have rollups are not consensus. Rollups are not consensus. They are using the consensus of layer 1. So I would say there is no equivalent to a hard fork in layer 2 because it's there is no consensus layer there. So I think does not apply.
No, what I meant is how hard it is for ZK-EVM for you to add new opcodes to it.
Oh, yeah. We probably that's this is going to be a stick to one opcode, and then we'll have to do we'll have to think about some mechanisms to upgrade but you will have to upgrade the full smart contract some way. EVM, so the EVM have some interesting opcodes just to detect hard forks. You can have the chain and you can have things. So maybe we can do something on that. We have not think very much on that.
Thank you.
That's interesting. It's an interesting thing.
So
I don't know.
Yeah,
Who's talking?
I'm over here. So I understand that that in ZK rollups that execution is a lot cheaper. So how do you actually price the opcodes in the ZK rollup?
We are going to try to maintain the same model that in layer 1. We want to keep, it's going to be some state variable here, it's going to be the gas. So we are going to try, at least at the beginning, to use the same gas cost that's in layer 1. What can happen is that maybe there is, because layer 2 is not exactly the same layer 1, and maybe there are some smart contracts that are more expensive to execute in ZK-EVM than in layer 1 and the other way around. But what can happen here is maybe there are some transactions that do not fit in the circuit, that are too big for the circuit and maybe would fit in the L1. We will see. But the idea is to maintain so from the gas perspective, just try to maintain, and this is, we need to maybe just think better, but the idea is to maintain the same gas model that we have in layer 1, so that developers, it should not make a difference between one and the other.
Okay, thank you.
Hi, thanks for the talk. It was really nice. So you mentioned it when you were first talking about the big polynomials and the Blockups. I'm assuming that the polynomial for the execution tray is going to be the largest one. If you have like one execution with thousands of upcodes, for example, I'm wondering even, of course, on-chain that's going to be very expensive, but if you doing the verification or the check that the polynomials, one contains the other, off-chain, how long does that take? I'm just wondering.
To verify, to build?
To verify.
To verify, polynomial commitments in general, in general are constant. So you commit to something is quite constant or constant logarithm. So it's just, and the verification so an opening do not depend on how big is the polynomial. Do not depend too much. Just in the start, for example, is log n. So it's just, but log n is just almost constant. So should not be, so for the verification, should not be an issue at all. And for the prover, yes, we will have more polynomials. It's going to be more expensive. So people is wondering for the prover. Yeah, the important question is how will cost to generate the proof of this. Okay. The cool thing here is that in polynomial commitments, but in any snark, in any zero-knowledge technology, the prover is, in general, is very, very, very parallelizable. So it's like you pay more. If you have a big proof, you just put more machine. It's going to be more expensive, and it will work. But it's doable. It's just a matter of how much will cost.
Okay, thank you.
Hello. How does the MEV fit in the context of the EVM ZK rollup?
Who fits in
like
what?
The MEV, the minor extractable value, is there any possible MEV that can be done in a ZK rollup? You mean,
so well, does a rollup?
Does the prover can arrange transaction in a way that it can extract value from those?
No. No. In general, depending on the coordinator selector protocol that you are doing. For example, in the one that we are using Hermes, we are using a kind of an auction to buy a time, to buy the 10 minutes slot. During this time, anyone can send as many, can verify, so can send as many batches as they can. Miners could try to delay that, but they will not earn anything on that sense. No, it's another story. But depends a lot. Here depends a lot in the mechanism that you are using. So the equivalent of miners, if you want in Rail 2, it's the operators, how you select
operators. It's more from the prover point of view than the miner, because I do understand that after that, when it's on the L1, it will be pretty much hard to change. But
they cannot chat, so the only thing that can do a miner, the only decision can take a miner is to mine a batch or not. If you didn't batch a batch, maybe the next miner will mine it. Here, if there is some collision between miners and coordinators to do some stuff, well, there could be something interesting to analyze there. But the other miner will have to do something else. We'll lose money just to do that, because it's not going to mine a transaction that's profitable to mine it. So at least there is a cost that will not. It's an opportunity cost if you want that's going to lose.
Other blockchain like Zcash and Celo are doing ceremonies to set up a trusted setup. Is that the same case with Hermes?
In Hermes, we are using Gross16. Gross16 requires a trusted setup. Actually, Plonk also requires a trusted setup, but it's a universal trusted setup. It's something that's run once. It's already run, so you don't have to worry about. And for each circuit, it's different. Here is, if we are doing these packing things, of course, if we are doing a Groth16 prover, Groth16 proof, we will have to run a trusted setup the same way we did in Hermes. If we are doing that in a Plonk, which is, then you will not have to do this trusted setup ceremony. Here is probably the best idea right now is to do it in Plonk, at least at the beginning of the versions, and maybe when something is stable and you just want to keep it as is and so on, maybe you just do Groth16, you optimize, run the ceremony once forever, and that's it. That would be maybe one approach, but something that both things can be done.
A little bit related to the previous question here.
Yeah, okay.
So if I'm a user I want to submit a transaction, do I submit the proof for that transaction as well, or is that the job of somebody else that is then putting transactions together in a
It's somebody
blockchain?
else that's gonna, it's the coordinator that's do all this job, and you will pay the fee for, that will go to the coordinator for that job.
So I can still not do it myself. Like, I want this transaction with this proof, do it.
Not in this, so not in this approach. This approach is send the transaction to the coordinators, probably, because you will have many coordinators. You have a decentralized system. You will send the transaction to all of them, and when they build the batch with all the transactions collected from you and from other people, we'll just do all these computations. Validators, we are thinking, so validators is not somebody running a Raspberry Pi in their home. Validators, especially in any rollup in general that are doing thousands of transactions per second, we are thinking more in investments of thousands of hundreds of dollars altogether. Just collecting, I don't know, 2,000, 3,000 transactions per second, sorting, ordering, creating these proofs, and so on. This is not going to be cheap. So the mindset for coordinators is another, it's just, we need to think, change a little bit the chip of a coordinator and maybe a staker or something like that.
And the proof is for the batch, not for each transaction.
The proof is for the batch altogether, exactly. So the program is taking as an input all the transactions that's securing. And one of the things that we'll do is just check the signature, for example. That you have to do it inside the circuit. But it's going to be a specific state machine that will do the signature verification. Actually, the signature we need it because, for example, we have this precompiled smart contract to check signatures. Okay, so we have to implement it anyway. So this super state machine for signatures verification is going to be another state machine, some polynomials, maybe with different steps, because verifying signatures, you have to do some maybe analytical multiplication. Each analytical multiplication maybe have different specific field multiplications, and you have like 2-3 levels of state machines that are linked together to verify a signature, or in this case, a set of signatures. This light.
Hey, what's about data availability? Did you find a solution to incentivize the data storage?
We are not focusing on data availability. So we are assuming that you have some sort of data availability. If I roll up, just put the data availability on chain, which is expensive. Okay? But here we have some promising solutions about data availability. One of those, of course, is Ethereum 2.0, sharding, and so on. This is one of the things. But there are, there are other people that's working on that. Well, you can have, of course, a federated set of servers, a kind of a Palladium on that set, or we can have even, I don't know, I think Polygon people were doing something about data availability. That's cool. And there are different approaches there. What we are thinking here as a rollup, we are a rollup. So what we are thinking here is to put all this data on chain, at least in the first version. But we hope that some other projects solve the data availability, because something that we need, not for rollups, but for many other things. Now maybe Filecoin, I don't know. That's a data availability solution too.
Is it possible for the coordinator, which is creating the proof as I understand it, to select the order of the transactions it's receiving? And like the use case or potential malicious use case might be that, let's say there's a DEX, it sees a bunch of large transactions come in, it inserts its own order ahead of them, and then inserts a sell order in front of them to front run that value.
Exactly the same thing that miner. Coordinator is like God for a while, so he can select. He's free to select transactions he wants, to sort them, and to include it in the batch. The same way that the miner is free to select the transactions he wants, of course, have an incentive, economic incentive, to include it there and include it in the right way. But a coordinator and a miner, they share a lot of things. So from running attacks are Well, we know a lot about that in layer 1. In layer 2, it's going to be the same. That done? Okay, thank you.